Okay, so chapter 20, right, is carboxylic acid derivatives. All right. Let's do some ranking questions first, right? So this is one of your textbook questions. It says rank each set of the compounds in order of increasing acidity. So for this chapter, I'm going to just be doing more or less, I think, the end of the chapter practice problems. Because a lot of these reactions, the reagents and stuff is very similar. Maybe I'll show you what I mean at the end of the textbook. Because the most important, I mean, there's like technically, I think there's maybe this 10 or 12 unique reactions here, but they're just all applied to different groups. That's all it is, right? But yeah, that's literally the one I'm doing, 20.35. Let's do that. Let's paste here, right? Oh, I don't know why this always appears so small here. There we go. It's better. Maybe it's what's it called? Okay, so rank each of the set of following compounds in terms of increasing acidity. So, everyone can see it, right? Okay, so I'll make sure it's all completely in view. Oh no. Oh no, that's a dead pixel. Oh, that's killing me. Sorry, it's just something I noticed on my screen right now, and now it's just gonna bother me. Okay, so acidity questions. Everyone remember Ario? I mean, hopefully you should, because it's probably going to be used a lot, and not probably has already been used a lot. If you're going to continue using it, so it's kind of similar stuff here. With the slight difference here is, in this case, these are aryl rings, right? So this is actually something that might you need to use. What's it called? Chapter 18 stuff, right? As the main thing is first, always look for the point of similarity, right? So here, if you want to kind of compare the most acidic protons, right, it's going to be the hydrogen. Oh man, wrong color. It's going to be the hydrogens off of all these things, right? Off the carboxylic acid group, right? And now really what's going to kind of make things more acidic is the conjugate base. Do we want the conjugate base to be more stabilized or less stabilized? More stable, right? And then as Ali said right there, that's a good way to also look at it is when you have these aryl rings or these kind of aromatic carboxylic acids, right? It's all about the electron withdrawing and electron donating groups, right? Electron withdrawing groups, right? They're going to make it more acidic because they'll stabilize the base better, right? And electron donating is going to be the opposite because they're adding electron density in, right? Which is going to make the base more unstable, right? So I guess if we want, we could do all the, you guys want to see the conjugate bases, or do you want to just do it based off the structure? It's up to you guys. I don't mind drawing them, but. Yeah, because literally without the bases, all it is just this, right? Yeah. So hopefully everyone's cool with it. You know what? I'll just write that. We'll just write this, 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 and this, right? So we could just ignore the hydrogen right now. Okay, so now we're just really just judging the strength of electron withdrawing groups. So out of all of these here, right, which one of these will be, so I guess we'll rank 1 most acidic. How many do we have here? 5. 5 is least acidic. So out of all of these groups, which one of these is the most powerful electron withdrawing group? N2O, right? So if we think about it, right, kind of when we have this negative charge, because this is such a powerful electron withdrawing group, right, could kind of think about it as in terms, well, technically it'd be based on resonance, but if I just drew a dipole, right, this would be partially negative. Yeah. It's going to be pulling the electron density towards the nitrogen, right? So let's draw that as a specific length. So I could just kind of compare this. Let's make it this big, like that, right? Oh, I'm talking about the original structure, like where the entire carboxylic acid, right, is most acidic. We're talking about stability of bases, so it doesn't matter. For this ranking, we'll just use this number system because technically I don't think he has a number system, right? So we'll just put this as 1, right, as most acidic, right? What's the next most powerful EWG here? We have a couple different answers, right? It's one person said the O-methyl, one person said carbonyl, right? Remember how you could always tell what's what is look at the lone pairs, right? Here we have lone pair directly next to the ring. That's electron donating. Here we have conjugation outside the ring. That's electron withdrawing, right? So the carbonyl is going to be the next one, right? And then what else we have here is technically ethyl and bromine too, right? Bromine is also electron withdrawing through induction, right? But it's not as powerful as a carbonyl, right? So here we could rank this as 2, right? What's going to be ranked 3 then between the remaining ones? The BR, right? And if I kind of drew the arrows here, right, they would basically get smaller and smaller. That's why I wanted to show the dipole is like this is going to get here, and we could draw this. And then now between the methyl and the O-methyl, right, methoxy, which one is going to be 5? Well, actually, yeah, Mohammed there is right? The O-methyl is going to be the least acidic one, right? Because that is the strongest electron donating group, right? CH3 is weakly electron donating only through hyperconjugation, right? Methoxy can directly, donate a lone pair in them, right? So this would be 5, this would be 4, right? And in terms of the dipoles, once again, right, this would be even smaller, right? And then this would be even smaller than that, right? So that's kind of why I want to show those arrows was in terms of the power of the groups, how much they're kind of withdrawing. If anything, for the last 2, it would be pushing the electron density really back towards, technically you could draw it this way, right? Because these are electron donating, right? So it would be pushing electron density back to the O minus there, right? So I guess in terms of acidity, right, if you do get something like a aromatic acid, right, it just has to do with EWGs and EDGs, right? I think the next question compares the different. Oh, the next question is pretty simple too. I'm surprised there's no questions with different. Is there not a reactivity question here? Thought there was. Guess not. Oh well. Okay, so if we go down here, right, 1 is going to be most acidic, 3 is going to be least acidic, right? Same thing. Got conjugate base stability, right? All of these have that similar carbonyl group. What's really the separating factors here? Right, so it's proximity of the halogen, right? So this is going to be mainly through inductive effects, right? So the closer you are to your, I guess, negative charge on your conjugate base, right, the better the stabilization is, right? Therefore, it's going to be more acidic, right? So this one is going to be 1, right? The original acid is the most acidic here because the Br is the closest, right? Here, the Br is 1 more carbon away, and the other one, it's 3 carbons away, technically. So this would be 2, this would be 3, right? So it's again 1 most acidic, and 3. Yeah, so just on your exam, just be careful of the way he uses the ranking numbers, right? I'm using 1 as most acidic and the higher number as the least acidic. Just read the questions, please, right? Make sure he's doing that. With the donating group, yeah, I guess you could say it. I haven't really seen those questions. But I guess like if you had something like OH, yeah, like a OME or OH, then you could say, I guess the opposite is true. I mean, like I said, it kind of depends, because then at that point you could also think about solvating effects too, right? Since they're technically not inductive groups. I mean, yeah, it depends, because I saw a question recently like that on an Orgo 1 exam, right, where it actually had nothing to do with Ario. The answer had to do with solvating effects, right? And really, at that point, it's kind of steric interactions, right? So when you have kind of electron donating groups and they're closer, right, technically you have steric repulsion, and when you're trying to have a base come and grab the proton, right? So it really just varies, right? That's why I don't like definitively saying like one thing is set for the other, right? Like in this question for aromatics, I could, definitely you could say EDGs do that. But like for non-aromatics, it really depends on the molecule, right? Because solvating effects is something you have to take into consideration as well, right? Okay, let's do a bunch of reaction questions then. It's 20.46. Oh. There you go. Let's do like, how many are these? 1, 2, 3, 4, 5, 6, 7, and 8. Let's do 2 at a time. I'm not doing all this practice questions. I'm just picking problems that cover most of these reactions. Practice problems are, and in this case, we are doing some of them, but they're mainly for your do on your own, I guess. But here, the inner kind of, there's a lot of inner chapter questions here. It's just, I don't like the way it's organized, right? For this chapter, it's just better, in my opinion. Always do all the problems that you can, but like the end of the chapter is nice. Okay. Mechanisms, mechanisms are pretty simple for all these kind of reactions. I can give you a generalized mechanism. It's what's called nucleophilic acyl substitution, right? So you have your leaving group here, which can be OH. Well, it's not really OH. Usually it's Cl, your anhydride. What else am I missing? It's your ester here, right? And I don't really want to include amides because they're not super reactive. But anyways, basically it's straightforward. Hey, your nucleophile comes in, attacks, right? Pushes this up. And you reform your carbonyl, right? Kick off, right? And then you have your carbonyl formed again with your nucleophile, right? And technically you could have a double addition in a lot of these. This was R, R, R. Some of these are selective where they only add once, right? So at this point, I'll just mention this is double addition. If possible, you'll have to see which ones are which, right? We'll go over all the reactions, like that general scheme at the end of the chapter, right after we do this problem. Nucleophile just comes in, attacks again, this, right? And then minus 2 nucleophiles here, right? and then OH. Literally this for more or less all of them. That's why I don't bother with the mechanisms for this, because it's kind of a waste of time, right? Yeah, so in chapter 19, it's the main difference is that the OH is kind of removed, right? Here, because you started off with carbonyls, right? But yeah, more or less it's very similar, right? The only difference there is you substitute and remove the carbonyl bond. Here, this is what we call nucleophilic. I guess it would be acyl addition. It's a nucleophilic addition, right? It's just on acyl groups. So I guess we could just call it nucleophilic acyl addition. I'll just write nucleophilic addition, acyl groups, right? And then kind of the main reason this happens is because all those leaving groups there, right, they're very good in terms of making that carbon very electrophilic, right? And basically you kind of just get alcohols for most of the products. And some of them, right, you can stop here, right? So we'll go over which ones those are. Some of these stop here after basically the first addition, right? But if it's a very powerful nucleophile, it's going to stop, it's going to keep going until it's fully reacted, basically. Okay, so let's do that back to that question here. Let's maybe move this down. Go in the way of all those notes. Okay, so first one here, right, is, what is it? LAH, right? What does LAH is essentially? What can we think of it as? It's a delivery agent for H minus, right? And right, Madrona, it's a reducing agent for carbonyls or carboxylic acids, right? So essentially what you're adding twice here, right? So we could think of this as H minus, what we're adding twice here is H's to this carbonyl, right? So it's going to come in, it's going to attach one H, right? And it's going to kick off OH minus. Actually, in this case, I think OH minus would be fine to kick off because you're in technically anionic basic conditions. But then it's going to come in again, right, and open up. So what is your in terms of substitution for your final product is what kind of alcohol is it? Primary, secondary, tertiary? Primary, right? So really all it is you could kind of think of this as you're removing that OH. I mean, technically you could say that OH, but really this carbonyl turns into your OH, and then what you have attached here, right, this is a single bond, and you have two hydrogens here, right? So here we have our product looks like what was attached here was the two H's, right? You don't have to show the H's, right? Obviously, when you just draw it like this, it's the same thing. I just kind of want to point it out because that's what the LAH was doing, right? And what's the water for in this reaction? What was the purpose of the water? Right, it was protonation, right? So before we get this, right, and this is right, well, technically we have the O minus, right? The oxide here, right? Why is water in a separate step here? Does anyone remember why water is technically a separate step when you use LAH? LAH is extremely reactive, right? So this is, make sure you, because I'm pretty sure you'll get points taken off if you don't put it thing. But yeah, LAH is going to react with the water, right? And you're gonna, I guess, technically form, yeah, H minus H2 gas, right? And it's gonna basically, if you have LAH present with water, it's gonna just destroy all of the LAH, so your reaction would never occur, right? So that's why whenever you're doing reductions with LAH, right, you have to make sure it's first usually inert, and on top of that, very, very water free. Like you have to flame dry your flask and everything. Like you gotta minimize any moisture in your reaction mixture flask, right? So that's the reason why the workup is a separate step. Okay, so here, B, we technically have two things. So step one, right? This is thionyl chloride. You know what, let me just use pink so that way I could write over this. So this is thionyl chloride, right? What does thionyl chloride do when it reacts with the carboxylic acid? What are we forming here in the first step? Right, so essentially, right, this is going to react with your carboxylic acid group, and basically it's going to form the Cl, right? So you could just think of this as literally just synthesis of your acyl chloride. So after step one, we're going to get this, okay, now the second step, right? What are we going to get after the second step? We have a amine here. So this is a dimethylamine, right? So we have NH, ME. What happens when you react an acyl chloride with any amine? Right, it's a SN2 type reaction where basically, right? I mean, it's basically just the nucleophilic addition again, but here your amine is your nucleophile, right? And what's the kind of functional group that you form here now? Close. Amine was from last chapter. These are called amides, right? Or amide, however you want to pronounce it, right? So it's that carbonyl nitrogen group like that, right? So here, all we're doing is we're taking our carboxylic acid derivative, in this case, the acyl chloride, and we're just, making it into an amide, right? So the structure is still the same. All that you really replace here, right, is now here. It's going to be Me here and Me here, right? And why doesn't the, kind of important to think about here, why doesn't the nitrogen attack again? Like basically, why is this only one addition? How are amides reactive compared to their other yeah? So they're not, right? The reason being is that nitrogen is an excellent pi donor, right? Compared to something like oxygen or whatever, where it's not as electronegative, right? And it's more willing to basically do this kind of double bond here, right? And that basically is kind of telling you that that carbon is not exactly very electrophilic here, right? And for that reason, right, it doesn't attack twice, right? It's because you form something not very reactive, right? And that's why you don't get double additions when you're doing amide formation, right? So that's why you can use an excess amount to just get your final product, right? And also, I guess another thing you could think about is also steric reasons, right? You have another NNME and like a NME2, the dimethylamine coming in. And you have all this bulk interacting here, right? So that's another reason, steric considerations. But yeah, reactivity of the carbonyl and steric reasons, I would say, right, is why the NME doesn't add twice. Okay, let's keep going down the list, right? Oh, wow, C is, oh, actually C is kind of, I don't know if you guys covered this one in class. I don't know how many reactions he did for the amides, because I know boson skips some of them. I don't know if Bisco does too. Paste this one here. You guys done with when thionyl chloride reacts with a amide? Do this reaction, or I don't know if it was not covered or not. You did. Okay. So what's kind of being formed here? So whenever you see SOCl2 reacting with an amide, what you could think about is this is kind of how would I say it? I don't want to use reducing or oxidation because technically that doesn't really change. Essentially, it's changing the double bond of oxygen to, I guess, you're saturating the carbon. Yeah, you could think of it as a carbon-nitrogen bond saturation, right? So essentially, right, what this does is when you have any amide, right, it's going to basically be making that carbon-nitrogen triple bond. So you basically cleave your carbonyl, right? Obviously, these are going to get removed, right? And you fully saturate that carbon-nitrogen bond, right? I don't know if the mechanism was covered for this class, but that's really, in terms of getting the final product, that's the kind of outcome you'd be looking at. Here, yep. And technically have to go this way. Why did I draw it like this, by the way? Going straight instead of drawing it like this, right? Well, that isn't exactly alkyne. It just has to do with the hybridization, but you're kind of on the right track, right? This is sp hybridized, right? No, like it's just to describe the nucleophilic additions, right? There are some specific, like the thionyl chloride, when it forms the acyl chloride, that's the synthesis of an acyl chloride. That's slightly different because it's basically thionyl chloride is interacting with it and like forms a bond, and then the chlorine attaches, right? I mean, like I said, I don't know how many of these mechanisms. Usually the main thing he's looking for is just understanding the products and outcomes for these reactions. That's why I don't really cover the mechanisms here too much, is because most of them are very similar and repetitive, right? And there's just so much material in this chapter. I've always found it better to cover the products, right? Like the reaction outputs, because it would literally take hours to cover every mechanism, right? That's why you have the lecture, right? So refer to your lecture notes and the, what's it called? Textbook if you want to see the mechanisms in more detail. But that other generalized mechanism kind of more or less describes most of these reactions, say like probably 80% of them, right? Okay, so that's all that happens when you have thionyl chloride and your amide, right? Okay, let's see what else is next. Okay, next one is I'll just draw it actually. I just realized all of these are almost similar. OME, right? So the first step is H3O plus. And the second step is CH3, COCl, right? And pyridine, right? So what's happening in the first step of this reaction? We have a ester, and we are doing what kind of reaction is the first one? We did this at the beginning of the session. What are they called when you just have an acid? Not really a aqueous acid, right? Hydrolysis, right? It's just so this is really just acid hydrolysis of an ester, right? And then for any ester, right, what do you get when you just introduce it to superacidic questions or conditions? What are you just turning the ester back into? You're hydrolyzing it, right? You're going to be technically introducing water as a nucleophile, right? This is the same question. I just wrote it out. So whenever you see any ester, so I guess generalized once again, OR, right? This is just acid catalyzed hydrolysis. And you have any H plus, or if you see H3O plus, whatever it might be, right? All you're really doing is just going back to the original carboxylic acid, right? And that kind of makes sense in terms of the name too. You're hydrolyzing it, right? You're trying to recreate OH basically, right? So any ester, when you hydrolyze it, goes back to its original carboxylic acid, right? And technically the other byproduct here would be whatever this R group is, ROH, right? So after step one, what kind of functional group do we get? Based off what I literally just said. What do we have here? COH, right? Cool, right? Now, what's happening in the second step? It's kind of, let me maybe draw out CH3COCl, right? If I drew it like this, maybe it's easy to see. Write it right. CH3COCl. Okay. Yep. Yep, pyridine here. What kind of formation is this? When you have a carboxylic acid, right, and you're reacting it with a acyl chloride, or what kind of derivative are we getting here? So maybe if I show you the first step, right, it's pyridine here. I'm going to deprotonate that. That's going to become O minus here, right? Now you have a nucleophile, you have an electrophile, right? Oops, let me draw these arrows a little better, right? This is going to come here, push this up, kick this out, and you form an anhydride, right? As was mentioned right there, right? So literally whenever you see that, and a carboxylic acid reacting with like a derivative, like I guess this is an acyl chloride. This would be your acetyl chloride, I guess technically. You're just
Pyridine is that ring, right?
the one I drew right below it.
Yeah, so the pyridine acts first and takes the H off, and then the one on top, the CH3COCl, then gets added to the rest of the structure.
The pyridine's the function of the pyridine is to deprotonate the acid, right?
Okay.
But then that makes it nucleophilic. You have a very powerful electrophile in the acyl chloride, right? Nucleophilic electrophile, right? They react. Cl gets kicked off like we showed before, right? In this case, the nucleophile is your carboxylate, right? And then you just form your final product, which is your anhydride. So O, this, and so this be your acetyl group there, right? Another way you can make anhydrides is technically also, what is it called? Through alcohols. Actually, I think that's the next one. No, it's the one after that. We'll get to it. Okay, so let's go down to E. We'll do some synthesis questions too with this, right? After we finish this question, I just want to go over all the reactions, the final thing, and how I kind of, when I did this way back, how I kind of studied for it. So we have OME here, and then we have, we have DIBA.
Can you scroll up for like a second?
Sure. Here you go. So what's DIBA similar to that we just did earlier? Right. Madrona said it's similar to LAH. Right. It's an H minus source. But what's different between DIBA and LAH in terms of reactivity? Well, both reduce, right? But what's in terms of the difference, right, is that one of them is what is it? It's kind of selective in how it reacts, right? DIBA, what's it called? Is well, the structure for DIBA is what's it? Diacyl butyl aluminum hydride. So I think structure should be something like diisobutyl. So isobutyl is this 2. So the Al should be in the middle. Yep. And this is H, right? The main thing is this is super sterically hindered, right? So what this does, right, when you have ester, right? Yeah, as people said, right, in the chat there, it's not as strong as LAH. LAH is stronger, right? Essentially, this delivers only one hydrogen here, H minus. So this is still H minus, it's just not as powerful. So it's selective that when you react it with esters, right, you could get an aldehyde, right? So normally if we used LAH, right, so let's, if we did LAH here, right, LAH followed by water, what would we get here? What kind of alcohol? Be primary alcohol, right? It would be the double addition on an ester, right? And we just get something that looks like this, or maybe for the sake of similarities, we'll keep the OH like that, right? So that's if you use LH. But now if you use DIBA, which is much more sterically hindered, like I drew over there, right? It can only add in basically one H. So basically, once you add in the H minus and kick off the OME, it's going to stop there, right? And then that means if you stop there, you still have a carbonyl, but you only have an aldehyde. So it's a selective reducing agent. I'm pretty sure it's only used on esters. I think maybe amides too, not sure. So here it would just be H, and then this would be your ring, right? So that would be your final product, right? So whenever you see DIBA, just think of H minus but once. This is what I was mentioning earlier, right? Is some of them are selective. They only stop after once. Another one of those is the cuprates. The Gilman, you guys learned about the Gilman reagents, right? You guys learned about Gilman reagents? Pretty sure you should have. What is it? Organocuprates, R2CuLi, copper lithium. Yeah, so this is called a Gilman reagent, right? It's similar in terms of a Grignard, right? The main difference is Grignard adds twice. And how many times does the cuprate add? Once, right? That's why I said there's really only a select few, but mechanisms and the kind of product outcomes are just, it's literally just a repeat of all this stuff, right? What's the next one up here? So F, okay. So we have phenol here. Let's keep going down the list. I think we only have 3 more left here. You have phenol here, and you have acid anhydride. So there, right? So if you think of this as ROH, this is your acid anhydride, right? What do you form when you have an alcohol and an acid anhydride? Which one of the derivatives? Right? This is going to kick in, then this is going to reform and kick this off, and you basically form an ester, right? So all you're really doing here is, doesn't matter which side you pick, but one of these carbonyls is essentially just forming an ester with the alcohol, right? The same thing if I use an acyl chloride instead, right? That's why all these are very, what we call analogs of each other, right? It's the main difference is reactivity, right? If I did this and then an alcohol, this might be a little easier to see, right? This will attack, kick it off, and eventually get deprotonated or whatever. And then you have your alcohol, your ester from there, from your acyl chloride. Same type of reaction. Now, the only difference here is this is your Cl group, right? The anhydride, right? So your final product here will just be, since someone earlier said to make sure we draw it on the same side, I will do that here. Right, that should be it. Usually I always like drawing my esters like this. B, H, that. But technically, just to keep things simple, right? This is the alcohol part. It reacted with this, right? Form that. And I guess technically you have carboxylic acid as a byproduct. That's not too important. The main thing is the ester, right? So yeah, that's that. And it's the next one here. We have diphenylamine, and we have acyl acetyl chloride. So here we have, I'm going to abbreviate this as NPH. And I drew out this entire thing here. So I'm just going to write this as this. Then what do we have here? So we have your acetyl chloride and then pyridine here. What's the function of pyridine here? PYR. Can't speak properly right now. Deprotonation again, right? So it's going to deprotonate the amine, make it a nice negative charge there. It's going to attack, kick in, kick off, right? The same mechanism I drew earlier. All you really is this is our group. Now what's substituted here is NPH, pH. Right. And the last one's a little tricky one, but I want to do one because I've always seen this, something similar to this last one on exams. Like from the last exam, he did use things directly from the textbook. So this is a cyclic ether here, right? I don't know. It's the one I have. I know you guys have like another one. It's the one I created. Should be in the link description for the WhatsApp group chat. Okay, so we have H3O plus here. So what is this kind of reaction again? What do we call these reactions? Hydrolysis, right? So we are essentially breaking up the esters, right? But now what's kind of different here, right, is that this is a cyclic ester, right? So whenever we have any sort of ester, right, OR, right, this is whatever R group, right, and we do hydrolysis on it, what do we get? We get the carboxylic acid, right? And we'll call this R1, call this R1 and R2. And what's the other byproduct, technically? The OR, right? So it'd be R2OH, right? So this is why it's important here when you have cyclic esters, because in a cyclic ester, when you hydrolyze it, right, the RO is still part of that entire molecule, right? So all you're really doing here, right, is you're going to be cleaving this bond, you insert water here, right? And then you're going to eventually protonate this as well. Boom, you actually got your final product. Let me actually drew that, right? So you cleave that bond, you form a carboxylic acid where the carbonyl is, right? And in this case, right, right? The OH is part of the same molecule. So it's something you still have to consider, right? And it's going to be attached, right? So if I gave you another one where I gave you something like this, another cyclic ester, right? Same thing here, right? Is we cleave this bond here, we form our carboxylic acid at the top, right? And then you have how many carbons? 1, 1, 2, 3, 1, 2, 3, right? And then that's bonded to other OH here, right? This ring opening reaction here. So whenever you have a cyclic ester and you're doing hydrolysis, you got to make sure, like, basically the ROH is important in this case. Normally, if you do any sort of ester hydrolysis, all you're looking for is carboxylic acid. That was the first question we did here. We weren't really too concerned about the alcohol byproduct, right? But here, technically, the alcohol is part of that same molecule, right? And same thing if I did something like, what is it? No, that's really it. Okay, let me actually.
Can you scroll up?
Yeah, sure. Let's go over early all these reactions, and then we'll do synthesis. We'll just end it there. Synthesis is definitely going to be on your exam, using all of these different reactions to start with something and end with something else. Like what I mean, multi-step synthesis. That's why you need to know all of these, right? Is that you're going to have to do a bunch of transformations, usually 5 or 6 steps, right? And gotta make sure that's why you need to know all the reagents. Like I said, there's only like 10 or 12 reagents. Like they're in the end of the chapter. Let's do that. Let me just pause the share screen right now and open up PDF reader. Which I don't know where it is right now. How is it? Okay, it's not there. To go to the OneDrive. All right, give me a second. Let me just find where I have the textbook on this computer here. Oh. So these are all the reactions in this chapter, right? Really don't want to edit this textbook, so to actually copy and paste it. Yeah. So these are all the reactions, right, in this chapter, right? There's the preparations and all that, but really, if you look at all of these kind of like the big O, because most of them are very similar, right? So whenever you have an alcohol reacting with a carboxylic acid derivative, you get an ester, right? We see that here, right? Let me draw lines maybe here, right? Whether it's an anhydride or acyl chloride, right? Same thing with the amines, all the different amides you get. If it's ammonia, a primary amine or a secondary amine, you just get different amides, right? LAH, you just get primary alcohols, right? Oh, that's the one, right? Lithium, aluminum trimethoxy or triethoxy hydride, right? So this is this was the one I was looking for. So LAI. So usually if this is like OME or OET, usually I think there's also O-propyl, right? That's what that is. That's the equivalent of DIBA, but for anhydrides and acyl chlorides, right? The Grignard, like I said before, right? Grignard does a double addition of your R groups, right? Same thing here, right? And the cuprates is just one addition, right? So even though this
What page
is
is that, if you don't mind me asking? Sorry.
here, let me zoom out.
And that's our textbook, yeah? Same
Yeah.
textbook. Okay.
This is
944.
944. This is every chapter has a review of reactions. This is how I did whenever, for every chapter, I would just go to this page and learn from this page. And obviously your notes too, right? So esters, obviously slightly different, but more or less very similar, right? Ammonia makes an amine, right? LAH, primary alcohol. DIBA is the equivalent of that, makes the aldehyde. Grignard, double addition. I don't think cuprates work on esters. That's why it's not included here. And then you have base hydrolysis here, right? So these are two methods basically to do hydrolysis, right? You could either do acid catalyzed hydrolysis of an ester or base catalyzed hydrolysis of an ester, right? Both outcomes lead to the same product as a carboxylic acid, right? In terms of preparing esters, right, they're pretty simple. It's either carboxylic acid and some sort of, actually, I think this only works for methyl. I don't know if it works for ethyl, right? So that's really for methoxy carboxylic acid. And then the other ones is just any sort of carboxylic acid. And this is, anyone remember what this reaction is called here? The one with the H plus? Called, this one actually has, it's actually a named reaction. Actually, these are both technically ring reaction, but this is Fischer esterification, right? When you take a carboxylic acid, introduce it into, you're right, Ollie, it's acid catalyzed stuff, right? But that one's called Fischer esterification, right? And then the last one is the same thing. The difference here is that this is, chlorides are more reactive, so you could use any alcohol here, right? Most of this is all repetitive, right? And then obviously you have the preparation and reactions of amides, right? So as you notice, right, acyl chlorides and acyl chlorides and the acid anhydrides, right, they are the most reactive, and all of their reactions are the same. So it's really just like I said, it's a total of a dozen different reactions, right? And they're slightly different, right? Okay. And then you have nitrile stuff there too, right? But I know like a lot of people look at the back of this chapter and then they're like, oh shit, this is a lot of stuff to memorize, but it's not really that much to memorize because most of it's repetitive. So this question right here is pretty good. Wait, no, this is not the one. They don't have one here. Here, let me see if I could find it. Let me pause the share. Get the solutions manual open. If you go to the solutions manual, right? This is really nice here, is basically it's a fill in the blank, right? In terms of conversions and stuff. So this is a good way to practice all of these reagents, right? Is do this fill in the blank stuff. And then whatever you're not good at, what you don't remember off the top of your head, right? You can just, work on those ones. So the solutions manual actually have a couple. Yeah, there we go. This is nice right here. So they'll fill in the blank basically. What reagents gets you from here to here, here to here, here to here, right? Oh shit, my bad, yo. Thank you. So what I was talking about is in your solutions manual here, right? At the beginning of the chapters, right? They have kind of like these blank fill in the reagent, fill in the product type questions, right? So here for like converting between functional groups, this is like a good thing. You could just fill in the blanks here. But then if you go down here, right? Once again, this is literally at the beginning of the solutions manual for each chapter. Like every chapter has this, right? Same thing even for the chapter 19, all fill in the blanks here, right? It's chapter 20, let's go down, and then you could just practice all the reagents like this, and everything you have trouble with is the ones you could work on, right? So these are pretty nice kind of like worksheets to practice all these reagents with. Well, the answers would literally just be this, right? So basically what it is like, don't look at this sheet, right? And just fill in the blanks here, right? That these are all the answers technically, right? But that's just to purely practice, right? If you know all the reagents and what they're doing, right? That's the point of that question there. Not question, the worksheet here, right? So like, you know, close all your textbooks, all your notes and everything, and you could just practice this. Then you could compare them to what you got right or wrong, right?
Sure.
Yeah.
From your experience on his past exams, does he ever ask us to put like the reagents, or we have the reagents and the reactant and then we just do the product?
I don't know what you're asking. Like you need reagents and reactants to make any kind of reaction,
My
right?
question is, does he ask us to identify the reagent we would use, or just he gives us like the first part of the reaction, we just have to find out the product?
I mean, depends on how the question asks. If he gives you a molecule and he gives you the the reagents, right? Then you have to see what the product is. For a synthesis question, you are given a initial starting material and a final product, and then you have to show every step, right? So there's two different types of questions, right? Usually it's, was it question 3 or 4 on your exam? You know, the one with 8 different reactions. That one you just have to write the major product, right? And then the synthesis question, you have to show every step with the intermediates and everything. Okay, so let's stop the share and let's do some synthesis questions to end on this session. Okay. Alrighty.
Sharup, do you know if we're gonna like see things from the first exam and the second exam?
I
Like
don't know,
the
not
major
really.
products and stuff?
Usually the synthesis questions are limited to the reactions of the products on, I mean, of the chapters on your exams. Like, though you could use like, you know, like old reactions you knew, like an E2 reaction or SN1 or anything. But yeah, as Mohammed said, it builds up though. And on your final, it's definitely going to be cumulative. But here, usually whatever chapters are in, I guess in 19, like reactions are in 19 or 20, those are enough to do your synthesis. I remember way back when I had Orgo too, but I had Andia, but he still did it the same way as Bisco did it, right? I ended up using like a Hoffman elimination, and basically I got like, I think the answer key had like 5 or 6 steps, but I basically got it in like 3, 4 steps, right? So if you remember our old reaction, it could help. We could do these. Oh, actually, technically they are slightly integrated, but I actually like this because this is kind of perfect for your exam. Let's start with A here. Okay, so we have a carboxylic acid, right? And we are turning it into, oh, this is a good question. It's actually, oh, this is kind of perfect in terms of what you will probably expect on your exam. So here we have this, right? And we are this. Okay, so propose an efficient synthesis for this. So, you know what? Let people take a minute or two to try to think stuff on their own, then I'll ask what people thought of, right? So one thing to note is, you know what, I'll let everyone just look at it, take a minute or two to digest it. Let's do this one together, and then I'll give you guys more time to do another one separately, like on your own, and then we'll compare. But okay, so what's one thing we notice? What functional group do we have in our product that we actually went over just at the beginning of today? Cyclic ether, right? And how do we get those cyclic ethers?
We can make them from ketone and to alcohol
Right.
using
Right.
hydrolysis.
So we use that diol there, right? And eventually, basically, we know that if we go, and this most likely came from a structure. Now, look, this is where retrosynthesis is very useful in these kind of questions, right? Right. This originated from something that looked like this, right? And we know this had to have happened because if we introduce basically this diol here, right? It's going to turn into that cyclic ether. Okay, so that means basically we have to get, excuse me, from the cyclic, the carboxylic acid to this ketone. Okay, can we go directly from a carboxylic acid to a ketone? Was there any reactions that do that or no? No, right? But can we make ketones out of any of the derivatives? Which ones? They're not the reagent. I was talking like the derivative, like a acyl chloride or acyl, like acid anhydride, right? Those are something that are reactive enough to form a ketone, right? And it's a good point you brought up the Grignard there, because when we get to that, you'll see why that. Think about that. This is a ketone, right? So we could say that from the first step, we can make an acid anhydride or acyl chloride. You know, generally for these questions, right, I would suggest to minimize the steps as possible, right? And to make it doesn't matter if you used an acid anhydride or whatever. I just always like using like acyl chlorides because it's just easier to never mess up the structure there, right? All it is replacing the OH with a Cl, right? How do we get from this to, let's actually probably have to go a little down this way. How do we go from a carboxylic acid to a acyl chloride? So Cl2, right? Cyanyl chloride, right? So you just use that. So Cl2, oh, not 3, 2. And we get our Cl, right? Okay, cool. Now Ali said Grignard, right? So if we do a Grignard here, it would be an ethyl Grignard, right? So it's gonna be, we're adding 2 carbons, right? But let's say we had this ethyl Grignard, MgBr, this would be in ET2, right? And then, what's kind of the issue when we have this Grignard is, remember, that's what I was saying, selectivity, right, is important here, right? We're trying to get a ketone. Does Grignards add twice or once? Twice, right? So if we did a Grignard here, what we would get, let me draw this in a pathway red, basically, right? Let's move this down here as well. Yeah, let's actually just put this over here. Right, is if we went down this red pathway, we're going to get ethyl, ethyl. I miss the bonds here. My bad, y'all. O minus, right? We wanted only one alkyl group because we're trying to get a ketone. Now here, the only thing you can go for is as a tertiary alcohol, I guess technically in this case, right? So the Grignard is not the reagent you would choose. Which one, if we wanted to install basically an ethyl group here, right? Which reagent can install our groups, but selectively and only once? What was that one called? The CuLi, right? Diva is for H minus, Sale, right? That's H minus. But the cuprates, right? So this is why choosing between the Grignard and cuprate is important, right? Grignard will add twice, right? And that's going to get you to your undesired product, because even if we protonated this, made it alcohol, you can't do anything with the tertiary alcohol. I mean, maybe there's some reaction that I don't know about where you could turn a tertiary alcohol and kick off the ethyl group, but as far as I know, no. Right, so you wouldn't go the Grignard. What you would do is the correct way would be to use the cuprate. So here, what's the R group in our cuprate? Ethyl, right? So it'd be ET 2CuLi, I believe should be it. Right, so that's going to get our ketone, right? Because now with the cuprate, it'll only add ethyl basically once, right? And then the last step is literally just this alcohol here, the diol. I think Eric was talking. If we started with the Grignard and then the diol, well, even if you start with the Grignard on a carboxylic acid, same thing is going to happen, right? If you started originally with a carboxylic acid and the Grignard, you're going to have a double addition happen again, right? It would still add twice. Yeah. So I think that's also pretty sure it's one of those. I don't know if carboxylic acids are reactive enough to react with Grignard. I think they are though. Let me just check to confirm. Well, they don't show it, but even if it did, right? It would add twice for sure, right? And that's kind of an issue here, right? And that's why we had to turn it into an acyl chloride, which has selective reactivity with the cuprate, right? And then this would just be this and H3O plus. Oh, H3O plus. I guess you could write minus H2O. I don't know if that. Do you know if Professor Bisco is like important on that Dean Stark thing? I don't know if he does or not. No, I'm gonna just leave it out. I've always been used to that, but that would be the total synthesis. So in terms of all the steps, let's kind of write them out on the side here, right? Your final steps would look like this. Carboxylic acid. So first step was thionyl chloride. Oops. Second step is going to be your cuprate. Right? Third step is going to be your and that should be it in terms of its steps, right? And then that gets your final product, right? Which is that cyclic ether. It's actually only 3 steps. So, but you could have done another route where instead of, what is it? Sorry, this is just wrong there. My bad. Instead of the, what's it called? The first step, instead of an acyl chloride, right? You could have done also. You could actually you could just heat this up and you would get a Well, actually, in this case, you don't want to heat it up. We just use, yeah, you could do this. You could do one, be some sort of base, pyridine or hydroxide. Second step would be your acyl chloride here, right? Right, and then third step is just the repeat. Now, the only difference between these two is what do we form after the first two steps? The anhydride, right? So 4 steps, like I said, I think if you're within 1 or 2 steps of his like approved one, or even like as long as it's not like 5 steps more than what he has on his answer key, you'll be fine, right? So this is also acceptable, right?
Can you do it?
What?
Can you like draw it out? The second part, like the alternative option?
The only difference is after these 2 steps. I'll only draw that structure. Literally the rest is the same. That's what you form after the first 2 steps. And then the other 3 reactions are the same. So it's going to turn that into the ketone. Ketone turns into the cyclic acetal, right? We will have a carboxylic acid as a byproduct. Or what? With the oh yeah, technically, yeah, but that's not too important. Like I said, it comes down to how many total steps. Like if you start thinking about true efficiency, like, oh, how to get maximum yield of products, then you have to actually go into like, use something called SciFinder. I don't know if you guys take an Orgo lab, you should have learned about SciFinder, right? Then you go look up a proper preparation to maximize your yield, right? But for the case of, an exam or a question like this, you're not thinking about yield after every step and byproducts like that. It's more about total steps, right? So that would also be acceptable, right? Is going the anhydride route. Okay, we'll do 2 more. So let's do yeah, we'll do B and C. They're not too bad. Okay, so start with B first. Give you guys a few minutes to do that. Oh yeah, B's a cool one actually. There's probably a lot of ways to do B. At least 2 or 3 I could think of. So let's move this down a little so it doesn't interfere. Yeah, they're getting an imine at the end there. So just think about how you would do that. There's probably a couple ways you could do this. I'll give you guys a few minutes to try that, and then we'll go over the way I do it. draw it a little differently. Maybe make things a little simpler to look at here. You're always like free to do this on your exam and stuff. It helps you look at stuff. Okay, let's go over how I did this one. So first thing, notice the final product is an amine. So I know it's amine if we do a reaction with an aldehyde, right? Aldehyde that looks like this, right? Going forward, you would just use something like right? It's the simple primary amine with an aldehyde, and you form an amine because of that, right? So basically, what you know you have to do is you have to get from an amide or amide to your aldehyde. That's I don't know. It's just gonna vary on your exam. I don't know what kind of mechanism you'll get. I mean, the mechanisms for these questions are just so simple. I wouldn't expect it. The most likely, like I said, it's usually some sort of acid catalyzed. Like last exam, you got the Friedel-Crafts alkylation, but that's still technically just an acid catalyzed mechanism. All he did was he gave you two groups, and then all you had to do was use the AlCl3 or whatever, right? Like I said, it's usually some sort of acid catalyzed mechanism to see if you understand arrow movement and electron flow. Okay, so we have to get from an amide to an aldehyde. So there's a couple of ways, right? We could basically, what I did was just basically turn this into an ester, right? So what you could start off with, right, in terms of we need to basically get back to a carboxylic acid, right? So I started off with that, right? If you just hydrolyze, because if you hydrolyze any of these, right, you get back your carboxylic acid there. So here, now we have a carboxylic acid, right? And I know I could get an aldehyde from an ester, right? Because of, what is it, with DIBA or something. I mean, technically, I guess you could use an acyl chloride or anhydride here as well. I just kind of thought of ester. Like, you know, amide to ester isn't too bad. So now you could do next step would just be something like, I don't know, we could use Fischer esterification here, H plus MEOH, and form an ester, OME, right? Now from your ester to aldehyde here, you could just use DIBA, right? I guess technically you need to work up step 2. H2O and your H plus there, right? So yeah, that would be the total synthesis here. It would just be total steps of first step is the hydrolysis. Second step is turning your carboxylic acid. So that basically at step 2, let me write this in red because this is where things could just change a little, right? This is the main thing that you could have done a variety of different stuff here, right? I turned it into an ester. You could have made this an acyl chloride and then, well, one second. Let me just draw out all of this first. MEOH. Then 3 was DIBA, followed by workup to form your aldehyde. Your final step is just your imine formation, which is H2 and ME. So we're gonna just, so here really at step 2, you could have done a different thing. Basically at step 2, let's say we went an orange pathway. It's orange, pink, right? We could have, I don't know, we could have made a acyl chloride. So then you get this structure, cyclohex ring, right? So now how do you get from an acyl chloride to aldehyde? There was a reagent for this too. It was also a variation of LAH. You could use something like, what would it be? Like a 3-step here, LIAL OTBU3. That's a common one, right? O-terbutyl. If you used LAH, right, we'd get a primary alcohol, right? So that's why we have to use like kind of, all right, no, technically there's also an H here, right? So then you could have just, and then this would be just workup. Then the rest of the steps would be the same, 5 and everything. So slightly different stuff, but it would also be perfectly okay to do, right? So that's why with these, you have a lot of options. Is with the carboxylic acid derivatives, there's a couple of different ways you can do stuff, right? And then basically this would be the rest of the SMAC thing.
What is the last step called?
The last step called the 5.
Number 5.
That's the imine, right? That's from chapter 19.
Okay.
And for step 3, what is the thing in the parentheses? I can't read it.
A little clear. OTBU. That's a common OR. Like you, I don't know if on your exam, if you'll be okay with this OR3, but that's one of the common ones is O-terbutyl, if I remember correctly. Let me just check in your book if they actually mention which one it is. They used OR.
And 3 and 4 would be together, right? Like it would be like 3 would be above the arrow and 4 would be below.
It doesn't matter. The above and below arrow makes no difference. It's this all it when you put a number in a thing, it's just indicative of separate steps. That's what it is. Right. You just have to indicate their separate steps, because if you had those in the same pot, right, or the same, like if it was all written as 3 as H2O, this would never work, because that would just react with water and destroy all of your thing there. Let me just see in your book if they gave you an example of, yeah, okay, they gave you the terbutyl. That's the one. That's the one that's commonly used. So in the book they abbreviate as OR3, but one of the most commonly used one is the O-terbutyl one, right? So you could have also done, instead of thionyl chloride, right, you could have turned this into an acid anhydride too, right? With the, like I said, there's a lot, and that would be what, 6 steps, but still it would be fine. Everything would be between 5 to 6 steps. So yeah, anyways, we're just actually gonna end here. It's like almost 2:40 anyways. So yeah, I think I said, I guess Monday night, I'll go over one of the exams. I have to decide what time. I'll probably let y'all know the day of. This depends on when I get back from the lab.
Is it gonna be the same link?
Yeah,